Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to be talking about another type of potential well that we can use to model molecular behavior. Specifically, we're going to be trying to use the harmonic oscillator to model molecular vibrations. So previously, we've assumed that all of our wells have nice straight sides, making a square well, where the potential may be infinite or it may be finite. So today we're going to be talking about a quadratic well. So this is one where we have essentially a curving behavior, where the center of the well will be focused on a value of x, and we're often going to be focusing on this in terms of displacement, because usually what we're using the harmonic, this parabolic potential to describe is going to be molecular vibrations. So you can imagine a simple molecule like N2. What we're going to do is essentially, because we can set any reference we want, we're going to essentially set this nitrogen atom as being fixed. So what this means is that we're going to find that the other nitrogen atom can move in other directions. It can rotate, and the whole molecule can move back and forth. But what we're going to focus in on is the vibration mode. So this is where this nitrogen atom stays constant, and this one moves back and forth. And we're going to essentially treat its resting position as a x value of 0. And what we're going to find is that as the nitrogen atom moves closer, so these two nitrogen atoms come closer together, we're going to see an increase in potential. And if it moves further away, we're going to see an increase in potential. So this means the most favorable position is right where it's at. But this doesn't mean that the object is ever going to stay still, because it turns out atoms can't. They're waves. They don't sit still. That's not in their nature. If the position is known, then known exactly, then congratulations, they're moving. That's our good old Heisenberg. And one of the things that you'll may notice is that these potentials are going to quickly become infinite, because again, not too surprisingly, these nitrogen atoms can't essentially fuse and become one, nor will I expect the bond to completely break if I go the other way. And it's worth noting that this isn't exactly the behavior of a bond, but it's not too bad. And so it turns out that this is actually a reasonable approximation for diatomic molecules. And most of what I'm going to say the next couple lectures is going to refer to explicitly diatomic molecules. We're going to later make some modifications of the system as we go to polyatomic systems, but for now, this is not a bad approximation. So the classical solution for essentially this kind of quadratic behavior is known as the harmonic oscillator. So this is the idea that's usually used to describe a spring. And essentially that's one of the classic ways of looking at a bond. Is it's a spring, but unlike a spring, it won't eventually run out of energy and stop. It's an atom, it will forever move. And so what we're going to find is that if I move my atom towards a positive displacement, it's going to have a returning force of minus kf. So this negative force means it wants to come back. If I have a negative displacement, well, negative position, negative prefactor, I have a positive force, meaning I want to move forward. And so this simple description of force essentially always means that I'm moving back and forth. Occasionally, I'll have no force acting on me when I'm at the center, but congratulations, at that point I'm all kinetic energy and momentum, so I keep careening to the other side. So this is a classic spring model. Now, using the model of a spring, according to Hooke's law, we can describe our potential surfaces, not too surprisingly, 1/2 kf times the position squared. So again, not too surprising that we have the position squared, as we have a quadratic potential well. This is literally the definition of a quadratic function, x squared. Now it is worth noting we have a 1/2 function dampening our force constant, but again, this gives us an easy way to go back and forth in between our restoring force, so the force acting on the particle at any point, and the actual potential surface. So again, it is worth noting that the potential at any given point won't be kfx squared. It's going to be actually 1/2 of that. So again, a fairly useful function to keep in mind. And again, where kf is just our force constant or our restoring force. It's essentially what's keeping the system in balance. So this gives us an expression for the potential of a vibration. This is actually fairly nice. However, now we've entered quantum mechanics. So I don't need potential, I need a potential operator. So I just take my potential function, I put a nice pretty hat on it, and since x is both the position operator and the actual variable, we're going to leave the hat off the other side. But again, essentially we relate in this case, we're relating our potential operator to the square of the position operator. So a nice simple form. Except for I don't need a potential operator, I need a full Hamiltonian. So what we can do is use this information to establish a full Hamiltonian. Because it turns out we already know the kinetic energy operator, this is going to be the same as it ever was. And we can combine this with our new potential operator to get a combined function. Where again, our kinetic energy is going to be dependent on the second derivative of the position. And the potential is going to be related to the momentum of the square of the position itself. So what we can do is try and use this to model essentially the movement of a diatomic atom, whether it's chlorine and hydrogen or nitrogen and nitrogen. And it turns out that this operator actually does have a well-known set of eigenvalues. And the eigenvalues follow actually a fairly nice form, where the energy is going to be related to a quantum number v. So thus you'll see EV. This does not mean it's the potential energy. Sorry for that, any confusion that may cause. It's instead the energy of the V state. So we have the quantum number V plus 1/2 times our good old friend H bar times omega. Okay, what's omega? So it turns out omega is what we call the vibrational frequency. So you can think of this as how fast the particle is moving back and forth. So that's actually kind of a nice feature. However, we often like having a more numerical valuation. So it's possible to get the vibrational frequency if you know the force constant and the reduced mass, where the vibrational frequency can be given as the square root of the force constant over the reduced mass. Now, for those of you without a lot of physics, you may say, what the heck is a reduced mass? Unfortunately, we're going to see a lot of equations like this where it's variables with inside variables. I apologize. So a way to think about the reduced mass is we're treating the system as essentially one atom vibrating while the other one stays constant. But then the question is, which mass do I use? Well, it isn't exactly the mass of the vibrating atom, because maybe in HCl, yeah, the chlorine being rather heavier is going to stay put. But in the nitrogen atom, well, if this one moves back and forth, this one's going to move correspondingly. And so we have to do is acknowledge that what we had really isn't vibration about one atom, it's about a center of mass. And so if I have uneven atoms, that center of mass is going to be focused near the heavier atom, and the lighter atom is pretty much responsible to all the vibrational mass. But if I have two atoms of similar mass, well, then they're both kind of vibrating equally, and this plays a little bit of havoc to our vibrational mass. And this is really where reduced mass comes in. So we can get the reduced mass by taking the product of the two masses divided by the sum of the two masses. So let's say that mass B is much heavier. Mass A is much heavier. Mass B is much heavier than mass A. Then what we tend to find is mass B is going to dominate the sum. And so consequently, since it dominates the sum, I have mass A times mass B over mass B. The reduced mass is just the lighter mass. If the atoms are the exact same weight, well, I'd have the square of mass A over twice mass A. So it would literally be the half of the mass of each individual atom. And again, we'll have a chance to practice with these a little bit later. But kind of to get an idea of what the reduced mass itself will be, is it will vary somewhere in between the mass of the lighter atom and half of the mass of the heavier atom. So it will be somewhere in between the two. Now, so this gives us a general set of functions for our energy, for the energy of the system. Now, one of the things that this has some interesting consequences is when we start to apply it to our actual energy levels. So the first question is, what values of V are allowable? Now, it turns out that unlike the particle in a box, it's actually possible for a vibrational quantum number to have a value of 0. So this is going to be our lowest possible value. And then we can have integer values above V. So we can start with V equals 0 and then work our way up. So this gives us an important property called a 0-point energy. Because as I said previously, atoms have to always be in movement. This means that every molecule will have some extent of vibrational energy, even if it's in the lowest energy state. So we can actually get the energy of our 0-point energy based on 1/2 h bar times the vibrational frequency. So this will be the inherent energy that will always be present in the atom. However, it is worth noting you can actually excite from one energy level to the state above you, and this gives us an energy separation of h bar times the vibrational frequency, because again, every state will be separated by this h bar omega. So this gives us a constant energy separation, which is actually a useful feature, and one of the things that we tend to rely on a lot when we're doing vibrational analysis, which we'll talk about in a little bit. So again, this is some big features you should focus in on the harmonic oscillator. We always have a 0-point energy, and every energy level has set gaps in the system, which it is worth noting is not something that we tended to find when we looked at a particle in a finite well. However, this just gives us the energy. Turns out we're also often interested in the form of the wave function itself. And it turns out the wave function of a harmonic oscillator actually gets a little bit messy. So we're going to see a lot of variables and variables. So we're going to start off with, we have, not too surprisingly, a normalization constant. And we also have an exponential function in terms of y, and I apologize for this, but you'll see that mathematically y becomes fairly useful a little bit later. And so y is just simply our position value over our alpha value, where our alpha value is essentially a ratio of the h bar squared over the reduced mass times the force constant. So this is going to give us a lot of the shape of the die-off of our potential. Now, this leaves us with one very important and kind of pesky variable. This is this HVY. So this is going to be called what's a Hermite polynomial. And we're expressing our Hermite polynomial not in terms of x, but instead in terms of y. And one of the reasons that we do this is simply to help keep our math easier. And it is worth noting that one of the pesky parts about the Hermite polynomial is they don't exactly have an analytical form. Instead, they're a well-known series of solutions, where our ground state Hermite polynomial is simply going to be a value of 1. And then we find a value of 2y squared minus 2, and so on and so forth in ever expanding polynomials. Now, the things I want you to focus on when we're dealing with the Hermite polynomials is two major things. They control A, the actual shape of the function, but B, kind of associated, that is going to be the number of nodes present in the function. Because it isn't too surprising, my ground state system should have no nodes. And congratulations, the Hermite polynomial for our ground state vibration is 1, and all that's left is a normalization constant and an exponential feature. Well, the exponential feature will always be positive. So it's going to be the second function that dominates the change from positive to negative, and more importantly, when we cross 0. This first function will never cross 0. It's always going to be positive. However, the second function with 2y is going to cross 0 exactly once, at 0. So in the middle of the well, we're going to go from a positive wave function to a negative wave function, which again makes sense, as this is going to help dominate the change in direction. Now, as I go to the next higher polynomial, I then go from no dependence on y, dependence on y, quadratic, then we go to cubic, quartic, quintic, and to a hextuple dependence, so a 6th order polynomial. So when we go to this 2nd order polynomial, we now have y squared, okay? This one normally will only cross 0 at 0, but we now have a subtraction value. And it turns out that this polynomial will actually will instead cross twice. And guess how many times the 3rd order polynomial crosses? Exactly 3 times, 4 times, 5 times, 6 times. And that's based on this combination of the order of the leading polynomial and then the subtractant feature. You can also notice certain patterns in that every time every expression, our dependence on y increases by 1. And then once we hit the 2nd order, we have a trailing feature that's 2 orders behind. So we have a second order dependence on y, and then a 0th order dependence on y, then 3rd and 1, then 4th and 2 and 0, and so on and so forth as we go down the series. And this leads to ever increasing crossings in the point. And because not everyone speaks in the world of mathematics, we can also examine these functions kind of visually. So our ground state system is simply a nice single bump, never quite goes to 0, asymptotically approaches it under long distances, and it is worth noting that we do see some tunneling into the potential wall because it is non-infinite at this point. And this essentially goes in between 2 classical turning points. So this is the point at which the energy of the system is equal to the potential energy of the system. And so again, we're going back and forth in between these 2 systems. Once we have our first excited state, we now have 1 node, negative in the negative region, positive in the positive. When we go to the 2nd excited state, we cross now twice, positive, negative, positive, and so on and so forth. And it is worth noting that we do have slightly different amplitudes as we go through these equations. And again, this is also dominated by the Hermite polynomial. So this is the 2nd function of shape besides the number of nodes. And one of the ways you can really see this is when, instead of just looking at the straight wave function, we instead kind of transfer to the actual population probability density of the function. So we square the wave function. You find at the ground state, most of the time the particle is located in the center of the box. But as we increase the number of states, especially you'll notice once we get to about the 5th excited state, we tend to see an increasing amount of probability density near the edges. And one of the ways to think about this is that as my as I give my system more and more energy, it's able to essentially move over a wider range, but this also means that it's moving much faster. And you can kind of think like a swimmer in a pool, that what ends up happening is you end up spending the faster you go, you're spending proportionally much more time at the walls because you have to slow down to do the flip, and then you can speed up, and then you slow down to do the flip, and then you speed up. So this isn't too noticeable when you're a slow swimmer, but as you go faster and faster, you're spending proportionally much more time at the walls than you are at any given point in between. And that's kind of what's happening when I'm oscillating. Now, one of the things we can then do is try and use these harmonic oscillators to determine some basic properties of our system. So the first thing we need to do is make note that even for my ground state system, I don't have a complete wave function. So I still have this normalization constant I have to deal with. I have most of the rest of the equation done with, but I still need to normalize the system. So we can do our classic strategy to normalize the system. I'm going to take the integral over all space and then set it equal to 1. So when we do this, I now have the normalization constant for the first state. And again, otherwise the system is fairly nice and easy. I go ahead and combine features. My constants are constants, so they come out front. And then the exponential should combine fairly nicely. Add the two exponents, and I'm reduced to e to the minus x squared over alpha squared. Now, this one ends up forming what's called a Gaussian function. So to solve a Gaussian function, you're pretty much going to need an integral table. However, it is worth noting one pesky feature of a Gaussian function is that they only have analytical solutions when you go from 0 to infinity, or consequently from negative infinity to infinity. However, under these circumstances, their solutions are fairly simple, and you can look them up in an integral table, which you will most definitely need. So the solution for this specific integral is going to be our normalization constant squared times the square root of pi times alpha squared, which, let's go ahead and distribute that square root. It's simply going to be normalization constant squared times alpha times square root of pi. Now, we have to think about what we were doing, and oh yes, we were trying to solve for a normalization constant. So we can rearrange the equation and get the square root of 1 over alpha square root of pi. And then you can go ahead and try and feel free to play around with the system. So this gives us a value of the reduced mass times the force constant over h bar squared, all to the 1/4, then to the 1/2. So you can kind of distribute that, and that would be essentially this inner term to the 1/8, and then pi to the 1/4. And feel free to play around with as you wish. There's a couple ways you can simplify this expression, but not too much. And it is worth noting, this is the normalization constant for the first ground state. It gets a little messier from there on out. However, there is an actual general solution no matter what V you're dealing with. So it is worth noting that we're always going to have square root of alpha times 1/4 pi. But we introduced two other special terms. We have 2 to the v, or again, v is our quantum number, and v factorial, all to the 1 over square root. So again, not exactly the prettiest equation we've dealt with, but as you may encounter as we move forward in quantum mechanics, we'll take any analytical solution when we can find it. So this is essentially our simple approach to the harmonic oscillator. We now have a wave function, we now have an energy, we now have a Hamiltonian. However, we'd like to know a little bit more about the system. So next time, let's bust out our operators and do some derivatives. Till then, take care.